Yeah, everybody got it. Recording. Okay, thanks everybody for coming this morning to the forum on robotics and AI for infrastructure management. We have today Dikai Liu, a distinguished professor at the University of Technology, Sydney. I think most people will know him. Otherwise, you're gonna know him very soon. His CV is too long. I'm just gonna try to summarize that. The guy's just been doing transforming robotics research into real applications here at UTS with a lot of success, actually, including autonomous robots for steel bridge maintenance, inspired climbing robots for confined spaces in a steel bridge, in particular the Sydney Harbour Bridge, intelligent co-workers also for abrasive blasting, and then smart hoists in the healthcare sector, as well as autonomous underwater robots for pylons in underwater structure. Since 2006, he has received more than 20 Best Paper and Research Engineering Excellence Awards. There's quite a few of them, but I'm gonna mention actually the 2019 UTS Medal for Research Impact, a most notable achievement given the pedigree of UTS, as well as the 2019 ASME Leonardo da Vinci Award, and the 2016 Australian Engineering Excellence Award, which is very notable too. His research outcome has been translated to industry applications too, including autonomous bridge maintenance robots commercialized through an entity, Sabre Automation Solutions, and the climbing robot deployed in confined space inspection, as well as the underwater robot. So, without further ado, I'll just pass that on to Dikai, and please go ahead. I'll ask everybody to file any questions that you may have as they come in the chat. We'll just answer them at the end, or just hold them, and you can answer them yourself. Thanks.
Okay, thank you very much, Jaime. It's very nice to get this opportunity to discuss with everyone about our research on intelligent robotics for civil infrastructure maintenance. Infrastructure is vital to economy and the community, and there's so many different types of infrastructure. For example, bridges are a typical kind of infrastructure in transport. In Europe, there are 42,000 steel bridges, for example, and also 210,000 steel bridges in the US, and 270,000 steel bridges in Japan. And in Australia, it's about so altogether about 5,000 bridges. Port infrastructure includes docks and many other facilities like piers, like the China harbors and the key cranes and many other facilities. Towers, a typical infrastructure in many industry sectors, like energy, like telecom. So, and also underground pipes and the drainage pipes are typical infrastructure in the water industry. Underwater structure, including bridge pipes, wharf pipes, and the underwater pipes, they are very important infrastructure as well. Oil and gas industry, or oil and gas infrastructure is vast and diverse, including the offshore structure, pipelines, and many other facilities. Maintaining such infrastructure regularly is very important to ensure and they extend the life of service. But unfortunately, at the moment in the whole world, manual operation is still the current practice. For example, for maintaining steel structures, like steel bridges or other steel structures, before applying new paint, we need to remove all the paint or rust, like what you can see here. But removing all the paint and the rust, grid blasting is a typical operation. but grid blasting is so difficult and hazardous for people to work, including the labor intensive, and also it's very dusty. You can see from the video here, and also low visibility here as well, and noise as well. The fine particles may contain lead or other chemical stuff. So it's very dangerous for people to do such kind of operations. Inspection and the condition assessment of bridges and the confined space, as you can see here, is very dangerous for people as well. You know, walk and hide, use the awkward body poses. You can see this two here, and also in the confined space, if there is anything going wrong, it's very challenging to rescue people. Transmission towers, like you can see here, inspection and maintenance is very challenging as well. Human workers have to climb the pole structure, and doing the cleaning and the painting is very difficult. You can see this person is doing cleaning of a transmission tower in Sydney, and they can work on the height and the very awkward body poses. It's very difficult for people to do this. It's very dangerous. Maintaining underwater structure may be even harder because of the harsh marine environment. Underwater structure normally covered by marine growth. In order to do inspection and maintenance, we need to remove the marine growth before do the inspection and maintenance. But removing marine growth in underwater environment, particularly along the coastal environment area, is very difficult. You can see that this diver uses one hand to hold a water jet to clean the surface, and the other hand to hold a rope there to make sure he is not being pushed away by the water current. So this is very dangerous. And so the critical issues, there are many critical issues related to manual operation of civil infrastructure. OHS, that is a very important one because of the hostile and hazardous work environment, extremely labor intensive, and the just lead-based paint in the fine particles in the air, and many areas are difficult to access or they are confined spaces. So work and height is another issue, and because of this, the cost is high, productivity is low, and the inspection and the maintenance is not complete. The results of the inspection and the inspection is very subjective as well. So a promising solution here is to really to supplement manual labor with robotic labor. But traditional industry robots cannot be used for such applications. Robots need to be capable of operating in environments that are complex, like this kind of environment here, or cluttered, or unknown, or partial known. And also the environment may change dynamically, like the underwater environment. So in order for robots to operate in such environment, enough intelligence is needed. There are many research questions we have to address before we can develop intelligent robots for such applications. Here are three of them. First one is, how can a robot move and support itself in such complex environments? So we need new design methodology here. Second one is about intelligence. So the robots need to be able to sense the environment, perceive the environment, navigate and build a map and localize the environment. And also environmental and operational awareness, motion planning and collision avoidance, level of autonomy, how much intelligence a robot should have in order to do such operation, a task. Learning capability. So third question is about robots work together with people. So in order to do that, we have so many questions to answer. For example, human models, how to develop intuitive human-robot collaboration and brain-robot interface. So those are the major questions that need to be answered. Then develop methodologies that can help us to develop fully autonomous robots or robotic co-workers that can work together with people. My research since 2003 has been focused on those three topics. The first one is infrastructure robotics, basically developing robots for infrastructure. Second one is human-robot collaboration, developing robots for various applications in manufacturing, aged care, healthcare, and in other industries as well. And the robot teams, like many robots working together in for container handling, warehouse automation, construction automation for different applications. So those research since 2003 has been applied in many applications. For example, bridge maintenance, port automation, manufacturing, transmission tower maintenance, confined space inspection and maintenance, and water structure and construction automation as well. So today, I just don't have time to talk about one topic, which is about infrastructure robotics. The first thing I'd like to talk about is design methodology. To answer the question, how can a robot move and support itself in complex infrastructure? We first look at the ants, because ants is very, very good at climbing and also get across obstacles, like what you can see in the video here. And also transfer from the vertical surface to the horizontal. And we designed an ant-like robot in the lab, and we did experiment. But unfortunately, this robot we found it cannot be used in practical applications, particularly like the application in the Sydney Harbour Bridge, because the capability of the robot to move around and also to have the payload to hold the tools for the maintenance. We also look at the Intuum, and we found the Intuum has a relatively simpler structure. Then we designed a prototype like this here, and they did a lot of experiments in line. For example, transfer from the horizontal surface to vertical here, and then from vertical to another plate, and then go through the manhole. And we found this one. We did a lot of research there, and we found this one really helped us in developing a climbing robot, which I will be talking about. Another research we've been doing here is really, we look at the birds climbing various structures you can see here. It's very amazing how birds can really climb. So they use the feet plus the beak plus the tail to balance it up, and also for the climbing. And also we did the experiment in an environment here, and then just analyze how birds climb this kind of collider structure. And we did analysis in terms of how the legs move, and also how the center of mass is kept, and how the beak is used, and when it is used with different angle or in, of the lidar. So for climbing truss structure, we look at how people climbing a truss structure like the transmission tower here. We really want to learn how human makes decision when he or she is climbing such kind of tower. How human just really make sure safety, how a person really keeps the center of mass or the gravity in the right place, and how energy is used when just climbing a structure like this. So we did a lot of experiments and analysis here, and say like we just put the markers on the climb here, and then analyze the trajectory. So this is a very interesting research. We have been hoping this research can help us to design a robot which can climb transmission tower. And this is part of the research we have been doing in collaboration with Tokyo Electric Power Company in Japan. So I will be talking about some results here. And so second thing is about intelligence. For a robot to operate in very complex structural environment, the robot has to have enough intelligence. So including sensor perception, mapping, localization, and the awareness of the environment and the operation. So in terms of the knowledge of the environment, a robot should have, and this is the robot should know the geometry, should have the knowledge of the details of the surface, and also conditions, and where the robot is in such environment. In the confined space, this is very challenging. So the robot needs to work out where to look at and how to explore, whether the robot has got enough information or not. So all those questions, the robot needs to make the decision. So what you can see here, this is the prototype robot in the Sydney Harbour Bridge, and they use the sensor to explore the environment to find the rivers, the plates, the connections, and for the next operation, like planning and the movement. So here again, here is another robot, which is the legged robot we developed in the for the Sydney Harbour Bridge, and the robot uses sensors to explore the environment, build the map, particularly the rivers, and also identify the space between the rivers, which is quite important for the robot leg to stick to or to push onto there. So again, this is about the knowledge of the environment and the planning as well. For underwater structure, then this is difficult, probably is more difficult because of the low visibility and the water current. So we built the map of the bridge path, for example, and we had a robot tested many times in the bridge structure around Sydney. And you can see here, the robot just move around a bridge path, use the sensor to collect the information, and they also to identify the marine growth around, on the surface. So then another thing is that the robot after the robot got the knowledge of the environment, the robot has to be able to do the planning in real time. So we look at the various planning approach and algorithms, and also how to handle the uncertain information the robot collected by the sensors. So this shows the planning, and also this shows a prototype robot in our lab and how the robot can move in this environment. Here is a prototype robot in a bridge structure, and then just move around in the river dense area, and also transfer from the ground to the vertical surface and move around. So, and we found, what we have done is quite good. And you can see here, even with this kind of environment with a lot of dust and rust, the robot can still stick onto it and they move around safely. So then go through manhole is another challenge, particularly in the confined space here, you can see here. And they say the robot needs to really get enough, really good knowledge of the environment before the robot can really stick to move around. For example, this video, what you can see here, this manhole is small and there are rivers here. The robot really to select where to step on and also to adjust to the step before going through a manhole here. So this is quite challenging. But yeah, so again, this is another robot, legged robot, and do it itself, goes through the manhole by itself. All what I'm talking about here is the robots are fully autonomous. All these decisions are made by the robot itself. So you can see here, again, this is in the real environment with our robots going through the manhole. Underwater environment, some underwater environment could be very complicated. So with a lot of structures there, then how can we get a robot, a mobile platform with manipulator, and then going through the underwater environment and make sure do not collide with the environment. So this is another challenge, particularly there are a lot of uncertainties in the harsh marine environment. If we have many robots working together, how those robots are going to coordinate among them. So then, for example, which robot is going to do what, and how the robot is going to achieve a optimal result as a team, not individual, as a team. So this will create the coverage problem by many robots. So another challenge here is about system development and integration. Many people have said, we have been doing a lot of research and publishing many papers, but to develop, to integrate a system and make sure the system can be used in real application is very challenging. I totally agree with that. This is a very, very big challenge here. So we had so many years of experience or failures as well to design very complicated systems. And it's a kind of system of systems. And you can say such a robot, and there's so many different modules in the system, hardware, software, electronics, and mechanical, and the sensing as well. So yeah, so this is just one example of a system, which is about the climbing robot we developed for inspection of confined space. So those are the research part. Then I probably will talk about several examples of how we applied our research in the development of robotic systems for practical industry applications. Here is the first one. We developed autonomous robots for steel bridge maintenance. This work was done back to 2013. So you can say this is a robot we developed here. And at the beginning, the robot is placed on a wheeled platform, which the robot can move around. Then our partners say, so they do not prefer a wheeled robot because when the robot is going to do the blasting, the reacting force from the nozzle is going to push the robot away. If the brake does not work well, then we start to use rail there. But again, this robot can be used on a wheeled platform. So the robot just uses the sensor to explore the environment, then build the map, and then based on the map, the robot starts to do the planning. So this is the planning, and then after the planning is done, the robot starts to do the blasting. Everything is done by the robot itself. We have two such robots in the bridge, and this technology has been commercialized, and also with sales in the US, Europe, and Japan, and Australia as well. So by doing this research, we learned a lot. So research questions and the enabling methodologies. At the beginning, when we start to do this research, we've had so many questions unanswered. And we don't have much methodologies there which can be directly used. So excellent research is quite important. Second one is algorithms in simulation can work in the live environment because we may not worry about the uncertainty. We may not be worried about the efficiency and the robustness. So, but for real implementation, particularly for real application, it's very challenging. So another thing is about developing robotic systems. This is a big challenge as well. And for a robot to be used in an infrastructure environment, one more question is how much prior knowledge should a robot have? Should a robot have? So whether this kind of prior knowledge is really available or not, the answer is no, because many infrastructure was built many years back. The kind of model may not be accurate because many changes have been made since it was built. So a big team and the big resources required for researchers and engineers as well to develop such robot. Second application here is about a robot for inspection of confined space. So this work was done in 2016. So this is the interim robot we developed for confined space inspection. You put the robot into the confined space through a small hole here, and the robot will use the sensor to get the knowledge of the environment, then select the safest way or the best way to go or to move. And when the robot, say a partition plate with manhole here, the robot needs to plan and work out the better way, the safer way to go to other side, to go through the manhole, and then come back. And all the information is collected and then just used for inspection. So this robot has been deployed as well, but we had so many challenges when we was developing this robot, and this really emphasized the challenges of developing robots for practical applications. So the robot was tested over 70 times in the bridge, which you can imagine how much effort we have, and the people have just put in. And every time we test the robot in the line, in the test rig in the line, which is a kind of 1-to-1 scale in terms of the size to the real environment. But every time we were confident saying the robot should work for next side trial. But as soon as the robot is moved to the real environment, this guys came back with a fail. So very little difference in the real environment compared to the live environment may cause a fail. So this is quite difficult. Design challenging, and as I mentioned before, not only the challenge related to the design of the body, but also with the adhesion mechanism. So this is another big challenge as well. So adhesion mechanism for different material, different structure, has to be different. And we designed a magnetic-based adhesion device, which can firmly stick to a structure, a steel structure. And if we want to peel it off, we have a mechanism. So we got a patent in the US and in Australia. Another thing is that we were lucky, and because design such robot we need a very powerful, small, lightweight motors or actuators. And we were lucky by that time, one motor came to the market. So the example of climbing robots we developed for infrastructure maintenance is a legged robot like this one. This robot has 4 legs, and then with the body, and in the front there's a 6-stop manipulator here. So of course many sensors installed under the robot. The robot can go through the environment, sense the environment, get the knowledge, and then decide how to go around. Very big challenge here is really about the rivers. So the robot has to really understand the environment with the rivers and step onto the space among rivers. That's a very big challenge. And also the pattern of the rivers is different as well. So after the robot gets enough knowledge of the environment and get into the location, the robot is supposed to, then the robot can just use the sensor, or use the tool to clean the environment. In this particular case, use a grid blasting, and also vacuuming the environment as well, and then do the painting after that. So again, this is a robot ready or developed last year, and now it's ready for deployment in real applications. So again, a lot of challenges flowing from there as well. Underwater structure. Underwater structure is even harder because of the structure. Could be timber, could be concrete, could be steel, and also the structure is normally covered by marine growth. So in order to inspect it, we have to remove the marine growth. And the marine growth is different from the water level to 5 meters in depth or 10 meters in depth as well. So the robot has to be able to recognize what material marine growth is and what is the better way to clean it. And this is the robot we developed and tested in many bridges around Sydney. And this is the experiment we did in the lab environment, how the robot move around a bridge pier and use the sensor to collect the information of the bridge pier and then identify the marine growth. So, okay, so this is the testing of the robot in the bridge around Sydney, or in the Lava Bean Lake. So identify the marine growth, then automatically work out a way to clean the marine growth. So you can say this is the planning done by the robot. And this is the cleaning of the robot. Again, everything's done, or all the decisions made by the robot itself in the environment. After the structure is cleaned, then the robot do the inspection, collecting the information. And you can see here, this is clean the environment, this is not clean. And so again, we identified many problems with this robot as well. So what the user needs to do, basically stay on the boat or around, and then to watch how the robot is doing. If the robot is doing something wrong, then people just can remotely change or interact with the robot. Again, it can be used in many other applications as well. So harsh marine environment, this is very challenging, particularly along the coast area. So the water current is very difficult to predict and quite strong as well, visibility is low. So this results that many available algorithms may not work well. So, and also how the robot can interact with the environment. So that is another issue. And we applied machine learning to help the robot to operate in such environment, particularly to remove or to reject disturbances and keep it stable and robust navigation as well. We developed many different generations of robots. You can see from the big and the simpler one into more complicated one. And this is the one that can be used, has been tested in many real bridges. So you can see in almost 4 generations of underwater robot for real we have developed. So one more application. Of course, different applications or different robots we developed, we have different challenges here. So this is a robot we have been developing since 2017 for transmission towers in power industry. So our collaborator is Tokyo Electric Power Corporation or company in Japan. So this research has gone through many stages and many iterations. Basically, what we've been developing here is really a robot which can either climb to a location in a tall tower like this one, climb up there, or is sent by other device or other system to somewhere, and then the robot uses the sensor to look at the surface of the structure in much more detail. Of course, you can think you have the drones to do the inspection, but drones can really stay relatively far away from the structure, and also particularly on the corners, the connections, the drones may not be able to look at, but those are the areas mostly get rusted the most or requires maintenance. So that's why drones and such kind of climbing robot can be combined. So drones can do a rough inspection, but this robot can be used to do the detailed inspection But even more, this robot can be used for maintenance, such as cleaning. So cleaning or to remove the old paint and the rust. Of course, we can use the plastic, like we did, you saw before. Or second thing, we can use mechanical tools, or like grinders. But all these are difficult. What we are looking at right now is really look at the laser system. Because if you are going to use a grid blasting, there's a huge amount of waste. This is this is not good for the environment, right? And then if you are going to use a mechanical way, like mechanical tool to clean it, it's very difficult, particularly for a robot to do it with high speed, high inertia, big inertia is very difficult. But use laser, it could be a good option. But of course, this really depends on the technology of laser system and laser technologies available right now. So we have to do a lot of research and experiment, both in the lab and on the site. So we have identified a type of laser that can be used. But again, currently the laser system, the productivity is quite low. But again, if you don't have a better option, at least right now, it is one solution. Another work we've been doing, we've been working with physicists or professors in physics in the Australian National University, and really developing new types of laser system which can really clean the surface much quicker and get a better quality, and also it does not hit the structure very much. So again, I'm expecting in 2 or 3 years, we can expect a much better laser system which can be used, will be available. So then we have the robot is available by that time, and then we have a good laser cleaning system is available by that time. Then you can say the technology or for the tower structure like this, with maintenance will be very, will be changed significantly. So this is what we've been doing here. After you clean the surface, then next thing is going to do painting. Of course, you can use the brush, and the moment you use the brush to do the painting, but in reality, you have to have people there, right? Human workers there. Then if you have a robot up there, then can we just use the robot to do the painting? For example, this is for the undercoat painting of the robot is doing. But again, for a robot to do the cleaning and for a robot to do the painting, the robot must have enough intelligence. And this kind of operation environment is different from the steel structure, because the members you can see here, different size, different orientation, connections here, and also it is not in the flat surface. And the structure is very sparse at the bottom, but once you get to the top of the tower, you have many more structures there, members there. So this is really challenging here, and we have a big team. We have been working on this and have formed a very big team work on this. So this is really, I like to acknowledge the support, very big and strong support from TEPCO Japan. Okay, one more application here, probably I just mentioned for Antarctica, and particularly for the climate research. In order to understand the climate change there, and also they need a robot which can go through the iceberg. Like, for example, if you imagine this blue plate is ice, then have a small hole, less than 300 millimeters, then we can put the robot in. Under this, the ice. Then the robot expand, and after that, the robot can really navigate around and use the sensor here to do various measurements, and then collect the information and then send the information up. So you can see here, so we are seeing the robot coming in here, and then this is another ice here, and the robot should be able to get to there and use the sensor here to do the measurement. So this is very cool application, because otherwise people have to stand here in the very thin ice, which is dangerous, and then put the sensor in, but the sensor can only look at the small area around there. But if we have a robot which can navigate a big, under this ice in the big environment, then the information collected by the robot will be significantly more than what a manual operation can do. And also, it's really just make it much safer for human work as well. And after the information is collected, then the robot can come here at the entrance point and then just come up. So again, this is what we have done in the live testing. This robot we need to develop this robot a lot more. And before this robot can be really tested in Antarctica. So again, this is another application, particularly of intelligent robots for different applications. Okay, those are the applications I'd like to mention today for the infrastructure robotics research. So we've been doing fundamental robotics research here. Really, they probably get the technology readiness level to 4 or 5. Then we have been doing applied robotics research as well to get the technology readiness level to 7, then translation. So closing the loop is quite important, particularly from research to translation to generate impact. And also by doing this, we get more research questions. And a lot more research questions, and we can formulate these research questions and get the postdocs and PhD students to do it. And this is another way to get more research funding as well. So in order to have a very good application, or in order for the technology to be accepted by real industry, because what they look at is really to solve their major pain points, right? So then you have to have excellent research. This is quite important. And also you have to be, to some extent, your research needs to be excellent and also has to be earlier than other people. Because otherwise, if everyone can do it, then your research may be behind or it's difficult to get it translated. So again, research team is quite important here. This is what the lessons we have learned, particularly related to development and the integration of the whole system. Engagement with end users. All the example applications you have seen here, we had significant or enough support and the environment, not only provide the resources, like funding or environment or test environment, but also people involved heavily in the project team. Their knowledge and expertise on the real problem is very helpful for the researchers to do research and to develop robotic systems. Again, another point here is that in order to get funding from industry partners, we need to address the pain points, address their pain points. If when we talk to them, we say this application is quite good and it's quite interesting, but by the end it may not go ahead because industry may not they do not have to solve the problem right now because it's not urgent. So pain points is quite important for us to address or to focus on. Okay, so I like to acknowledge many people, and all what I presented here is the outcome of many people's research. I've been working pretty much with everyone in the Robotics Institute, every academic and in the Robotics Institute, and many research students and research fellows and research engineers contributed to this project. And the undergraduate students, it provide a very good way to train undergraduate students as well. So I also like to acknowledge the Roads and Maritime Services of New South Wales, Forward Technologies, and the Cyber Autonomous Solutions, who is the one commercializing the blasting robot, and the TEPCO as well, and also the Australian Research Council. Okay, so thank you very much, and the questions are welcome. Thank you.
Thank you, Lisa. Sorry, Dikai. That was a very interesting presentation. And so many projects, actually. I'm obviously aware of it, but I think many people here might not be. So great, great presentation. All right, so we have, yeah, right on time also, Dikai. We have a few minutes left for questions. Anybody has got any questions, please feel free to unmute yourself or put them in the chat, and I'll just file them through. Right, while we wait for some of them, I'm sure they will come through. So, oh yeah, no, we have two people here. Yeah, sorry about that. Yeah. Who is actually up? Who raised the hand? Two people. I can see the hands actually. Oh yeah, John. Yeah, please go ahead, John.
Thanks, Dikai. It is a fantastic presentation again. So the robotics, Japan has developed a lot of bio-robot, like a climbing robot, snake robot, but they never had the successful application. So we always treated them as like just a hobby-like research. But this is truly the exciting that we combine that to real application. So my question is a little bit because in the COVID time, we lost a lot of technical staff. And then do you have any idea how to keep your expertise? Because our technical staff, if they left, then it's pretty hard to continue the research. So what's your comment?
Yeah, this is very challenging. Everyone is facing right now, and we lost many people due to the COVID, and the projects are delayed. For example, the project with TEPCO has been delayed, and also the project tasks have been changed due to the restriction of international travel. So yeah, it's very challenging. The only way we can do a good point. Okay, there are two aspects. One is good point is that we are graduating many PhD students every year, and there are the resources, which very important resources we can really just have, and we should just keep doing that. Like what many research engineers and postdocs all graduated, most of them all graduated from our research institute. So this is a good, this is a very good resources, and also they are trained. We have been training them many years, and they are ready to contribute. Second way we have to look at is really to recruit people from outside. I think this is a way we have to look at. Otherwise, I can say, particularly currently, the financial challenges everyone or every organization has, it is quite challenging, of course, yeah.
So outside means industry?
Yes, industry or probably graduates from other universities, for example.
Thanks.
Thanks, John. Yeah, we're all suffering that actually, to be honest with you.
Okay, yes.
We have Chao also with a question ready to go. Thanks, Chao.
Hi, hi, Dikai. Thank you for this fantastic presentation, and also congratulations to all these achievements you have generated.
Thank you.
So, one question is that I see that you utilize a human's gesture to mimic human's gesture for that climbing robot on the tower. So my question is that we a big difference and between the biomechanics of human body and also the dynamics of robotic system. So I want to understand that how did you fill this gap between these two differences and adapt to humans' gesture? Thank you.
This is a very good question. Thank you very much, Sean. The way we have been really look at how people or how humans climbing truss structure, the questions we've been trying to answer here is really how people or humans use their four limbs, like the legs and the arms, and how they're going to select where the arm or which member they're going to choose to to climb up or to stay on. And also the center of gravity or center of mass. How do they keep the center of mass? For example, for people climbing the transmission tower, which is different for people to the rock climbing, and for the rock climbing is even harder. So we did analysis as well. So at the moment, we have not really get under the stage that we like the robot arm really to imitate the how the human arm is really, for example, the pose or the movement like this, by combining the biomechanics model of the human arm and also the joint, the skeleton. But we have not looked at that yet, mainly because we thought if we're going to design a robot which can mimic the human arm motion in the transmission tower in such kind of complex structure could be difficult. And we have not really started to look at that yet. What we really look at is that the selection of the point, start point, the end point, and then in terms of how a robot arm, move from the start point to the target point, which is based on the capability of the robot. It's not based on how human did it, and then we control the robot to do it. We have not get to that stage yet, but that is a very good question we can look at in the future. Particularly, I mean, because when human apply this kind of pulse or doing this kind of operation, they are really trying to minimize the energy. And so this is a very good point for us to look at. But unfortunately, we have not started yet. But that gives us a good direction. Thank you, Chair.
So thank you, Dikai.
Don't see anybody else coming up with a question. John. Yeah, John was making a comment in the chat that by inspiring climbing wouldn't mean human-like, I guess. We can have 5 arms or 6 arms or even different mechanisms, which I think, yeah, we all agree.
Yeah, this is a very good point. Particularly, for example, when at the beginning, we look at the birds and how birds do the climbing, and we look at the different systems, but we found theoretically, you can have very small number of legs or arms you can do the climbing, but practically it's very difficult. So because you need the robustness, you need the reliability, and also the robots need to have the capability to hold a tool or to interact with the environment, and all this, if we take all this into account, then 4 arms may not be enough. But even with 4 arms, you have at least, when we control the robot, we can keep 3 arms always in contact, which means you form a triangle to keep the robot stable. Then you move every time you move 1 arm. But human may not do that, right? Human may have the body and arm moving at the same time. So again, the robot is not capable of doing that. And the point made by John is very important. Say, we can have 5 arms. For example, the torso, we can put arm in the torso, a very simple arm. Could be 2 or 3 degrees of freedom. But this arm could be really just used to really to keep the robot stable in a particular position. And so definitely, so there's so many questions to answer. And this is the this is the area which has, we can do a lot more research here. Okay, thank you. So I guess we are on 58.
Chan, sorry, hang on. Chan has got an extra comment to add, please.
Okay, cool.
Oh, sorry, I just sum up.
Sorry, I thought you were raising your hand. Sorry about that. Actually, I do have, we got a couple of minutes. I do want to actually ask you something myself, Dikai, because you've actually done so many industry collaborative projects, and there's various schemes that you can actually take advantage. And we have actually quite a bit of industry presence in this chat today. I'm just wondering what's your insight into the most leveraged way that industry can gain advantage of this collaboration with us, universities in general, in these collaborative projects. What's your opinion? Because you've tested them all, I guess.
Yeah, it's depend on the industry and what our partners are expecting. Some partners are more forward-looking. For example, they have a technology they think 5 years they need a kind of technology and they like to start earlier. This is similar to the TEPCO scenario. So you say we've been working with them about 4 or 5 years, and then they, at that time, back to 2017, they said they like to have many robots to do the maintenance in 8 to 10 years. So for this kind of partner, then we can really have a little bit more, the collaboration can be just really forward-looking. For some industry partners, they more look at and say, I have a problem, this problem needs to be solved. So, for example, for the Patrick Stewart holdings, they have many robots in the port, and they like to have the coordination algorithm which can be used to maintain for the coordination of the robot. So, in that case, that kind of project has to be a little bit short-range project. So, definitely engage with them, try to understand what they're thinking, what they speak, and also use the same language with them. I think that is the one really I found it's quite useful.
All right, thanks, Dikai. All right, so we'll probably move over to our second speaker today, Andrew. Maybe if you can start sharing your screen, I think you should be able to have that available to you.
Kia ora all.
Yeah, there you go.
Andrew Renton from Transpower, Senior Principal Engineer here at Transpower.